Hi, my name is TJ Rodgers. I'm the chairman of Enovix. I've got a bachelor's degree in chemistry and a PhD in electrical engineering, and that qualified me for years to be confused about the technology, which is pretty arcane. But with 10 years of learning and having to figure out a lot of the stuff for myself, today I decided to send a message to shareholders on BrakeFlow technology. We have that word. It's extremely important technology, and I think it deserves a slow explanation to explain why I think it's so important. So that's the purpose of this video. Okay, fires are a big problem with lithium-ion batteries. Have been for a long time. You read about them all the time. The incident I'd like to talk about, just to calibrate you, is the cell phone battery disaster in 2016 to Samsung. Now, Samsung is an extremely competent, world-class company. So if they have this problem, any company could have it, and all companies deal with it all the time. These are the headlines: CNN, FAA banning Samsung Galaxy Note 7 from all flights. And then at the end of the thing, LA Times, Samsung Galaxy Note to cost at least $5.3 billion. So this is a big deal, and therefore solving the problem is a big deal from a corporate point of view, and I don't think that's clear to the public. Okay, so we're here in Enovix's Reliability and Safety Laboratory, big room full of equipment that is used to test batteries. And in this case, I'm going to show you about how shorting in batteries and fires work. We bought this phone at the local electronics store. It's a standard Android phone, and took the battery out of it. Now we're going to play with that battery and illustrate the points. First of all, this battery has about 10 watt-hours of energy in it, and that's a lot of energy, but you wouldn't tolerate any less energy because you want your battery to run all day long. So if I put that much energy in this battery for you, what does that mean? Well, first of all, let me show you what it means when you short the battery. So this is a nice switch, pure copper, and it's a dead short. It's a 1 milliohm, 1,000th of an ohm short. And I'm going to put the shorting device across the battery. Okay, now on it I'm going to put a thermocouple. So this is a bead of metal that's used in a lot of industries to measure temperature. The temperature measuring device is right here. So right now that thermocouple is at 22 degrees centigrade. And we also have a current measuring device across that resistor, and right now that's jittering around because there's no current. Okay, so when I flip the lever, I'm going to short those two terminals of that battery out. And the first thing you're going to do is see current and then temperature. I'll point that out to you. And then I'll show you one more thing that'll be kind of surprising. Here we go. Okay, 50 ohms, 50 amperes, 27, 28, 29. Picture, please. And there we got the thing red hot. Okay, so that battery in about 10 seconds heated itself red hot. That wire was like a filament of a light bulb, right? We were burning 4 volts times 50 amps is 200 watts. Well, a 100-watt light bulb lights up bright white. And that's what happens when you short a lithium-ion battery. First of all, I'm going to show you how to protect this thing. This is well known. This is a resistor, a 1.5 ohm resistor, and using a resistor to limit the current is a well-known way to protect devices like this. Okay, so all I'm going to do is take my short, and I'm going to stick a resistor in series with the short. Now, when I flip this, the current's going to go up again, but the temperature's not going to go up because that resistor will limit the current and limit the power that runs in the circuit. Are you ready? Here we go. Now we're drawing 2.7 amps times 4 volts is about 10 watts, so that's the right amount of power. This resistor will warm up, and that thing will run all day long, and you can see the temperature's even dropping down as we're talking. So here, this will run for 1 hour, that 10 watt hour battery and a 1.5 ohm resistor. So this is normal operation where this is the load. So you say, okay, if I can use the resistor, maybe not that big ugly one, to protect my circuit, I'm home free. All right? So let's do that. So now we've got the battery. I want to check and make sure it is still good, given that we lit it up. And so I'll actually try to light up the phone that it came out of and show that it's still working. And all right, so there I've hooked it up, simple enough. And turn it on. And there it goes, and there it is. It's all the way booted up. The phone's running. Okay, now, if I wanted to protect this phone, what I would do is I take my protection resistor, 1.5 ohms we talked about, hook it up, and then I'd hook up the phone through the protection resistor. So all I've done is add that resistor. Now we'll do it again. And there it's starting to boot up. And it's locked up, and it won't boot up, and there it went off. And the reason is 4 volts coming out of the battery drops down to a little over 2 volts coming out of the resistor, and it's not enough voltage to run the phone right. So although this low-valued resistor can protect the phone, it also prevents the power you need coming out of your battery to run the phone. So that's the real problem. How do you protect this battery yet have enough power in it to run the phone? So here we used an experimental apparatus to short the battery to make a point. In the real world, to short a battery, to test it for reliability, you literally crush the battery, or you poke a conductor through the battery to put the short on the inside. You all saw the battery get white hot before on the outside. The worst case is when the battery gets white hot on the inside. And then what happens is the plastic melts and the anode material comes in direct contact with the cathode material, and when they touch each other you get a fire, a real chemical fire on top of just the heat from a short. So that's the worst test, internal short in a battery, and that's done with a special machine that we use to test our batteries. I'd like to explain, remind you how a battery works. Okay, this is a lithium-ion cylindrical battery. It actually is a lot like that one, except instead of wrapping the anode separator and cathode around a round form, this battery wraps those 3 layers around the flat form. Same battery. And the inside of that battery, we took one apart. It looks like this, and as you unroll it, you find 3 layers. You find copper in the anode, the plastic separator, which is a thin film of plastic that separates the anode, and then the cathode, which is formed on aluminum foil, about half the thickness of the aluminum foil in your house, with the cathode material on it. And this then is in a jelly roll, in this case a flat jelly roll in this battery, and the bad test is what happens if you get a short in the middle. And that's the test we're going to show you right now. It's not an external short one end to the other, but a short right in the middle of the battery, like you crushed it in some way that would cause the short in the worst possible spot. So we've got the battery out of the cell phone here, and we're going to short it now, not externally for a demo, but we're going to short it internally, which is the worst case, and see what happens. The way you do that is this machine called battery crushing and nail penetration machine. It actually makes something like that. And what it does, it takes a stainless steel nail, pokes it through the battery, 1.5 tons of force, and then that gives an internal short to the battery, which gives the most chance for the reaction of the internal components of the battery. We've got just a little bit of instrumentation. We've got a thermocouple to look at the temperature of the battery. And we've got a voltage to look and make sure when the battery's shorted, because you don't want to take these things out until they're discharged, because they're still dangerous. Okay, so this is a machine. Shut the door. Turn on the hydraulic system. And here we go. Okay, you got smoke. It's already opening up. Sparks coming out, bright red, so that you're looking at 800-900 degrees centigrade. Now it's on fire. That is a fire coming from the disintegration of the cathode material, oxidizing anything burnable, but primarily the lithium in the cell. You can see on the left side the thing is red hot, and our temperature I guarantee our temperature is not 28 degrees. The reason is that the thermocouple evaporated at 400 degrees centigrade, so this is like over 1,000. You can see, stuff splattered all over. So this is a classical fire that happens when you crush or penetrate a lithium-ion battery, and this is what you're trying to avoid. So then the question is, what's the BrakeFlow device going to look like? That's what we invented BrakeFlow for, to get rid of that. Okay, so we've got the BrakeFlow battery in here now, put in the new nail, and we're ready to puncture that battery. Normally this chamber is sealed and it gets splattered with a lot of stuff. In this case, we ran some wires in through the door, so we're going to run the cell phone, we're going to look at the temperature of the battery, and we're going to look at the voltage of the battery. And in order to see what's happening during this. Normally, it wouldn't matter. The battery would start burning within seconds, and that would be the end of it. Okay, so I'm going to lock this one in to a test you've seen just a few minutes ago. Okay, so we now got the battery in the chamber. It's hooked up to its cell phone, and we're going to start up the cell phone. So there, the cell phone is booting up. Battery's at 25 degrees, and the battery is 4.22 volts, so it's fully charged battery. That's always the worst for a fire test. All right, hydraulic pump on. Test, go. Okay, nails in. Phone still running. Phone just died at 2.4 volts. So the short drew down the battery. Temperature's going up to 32. Not much activity. We can see some electrolyte coming out. Temperature's up to 38. So we're now running amperes of current, tens of amperes of current through 1.7 volts. Temperature's still going up. It's 42 now. I see a little bit of gas coming out. There's a little bit of swelling. Temperature's up to 47. Voltage is down to 1.7. So that battery is still a functioning battery, but we have a device which needs like 2.7 volts in order to operate. Temperature is climbing more slowly now, 53 degrees. Battery voltage is down to 1.8 volts and dropping. The rate of rise of the temperature is slowing down. By the way, this battery will degrade at about 170 degrees. That's when the separator melts. And that will cause an even quicker reaction. But this thing is 110 degrees below that temperature, and it will never get to that temperature. Can't see much. That, of course, is what we expected, that BrakeFlow would prevent burning. And people have been working on this since the lithium-ion battery got invented. This has always been a problem because there's so much energy in the battery. You have to have a mechanism for releasing it slowly because it will heat things up. So right now, it's over and nothing happened. This changes the danger you face if there's any catastrophic event, crushing or penetration of your battery. And this is the only technology I'm aware of that can do this. So let me summarize. The standard cell blew up in 4 seconds. It got up to 283 degrees before the thermocouple stopped working. And as you can see, it was actually splattering red-hot debris around. The BrakeFlow battery, this picture was taken in 4 minutes. It got up to a peak temperature of 75 degrees centigrade, which is 95 degrees lower than the temperature at which the separator would melt. So this is a big deal. This kind of, and I'll show you some data from outside, this hasn't happened before. Okay, but the question is, how do you pull it off? Because we know resistors don't work. Here you can see a battery that's unfolded, and you can see the insides of it, and you can see the copper anode, the plastic separator, and the aluminum cathode. And this is a sandwich in the middle. And what you can see is there is no way to do anything other than put in a big resistor in series with the device. And we already know that resistor will cease functionality for a cell phone. You can't do it. So how do we get it done uniquely, BrakeFlow in an Enovix device? Okay, this is a strip of anode material, copper's anode, with a black goop on it. And in this case, it looks like a piece of film. And that film is for our machines to run it. But if you look, you see here that the anodes are separated from each other. So where there's one large anode in a conventional jelly roll battery, there's 100 individual anodes, and that's how we get our job done. What I've shown is this thing cut off right where the line A is. And you can see the little copper connectors for each of these anode strips. 100 of them make up a battery, 10 watt-hour battery. And then the question is, how do you put a resistor on each one? We already know that a 1.5 ohm resistor will do the task, even for a whole battery, so obviously that will do the task for a smaller battery. And therefore we're going to have 100 1.5 ohm resistors, and that really is the secret. We hook up a 1.5 ohm resistor to each section of the battery, and that means we have 100 of them. And when you have 100 of them in parallel, each one will protect the anode that it's attached to. But when you have 100 of them in parallel, the resistance is 100 times lower, and that's how we don't block the current going into the cell phone. Let me show you now how we stack our batteries. This is an actual movie of a piece of equipment in the factory. Here you see the quote-unquote film moving through. These are the anode strips. You can see them there. And this is how a flat piece of material gets stacked. And you can see them getting punched out. And then from the other side, you can see the stack is right there, the stack getting formed as the resistors are punched into it. And when you're done, you end up with a stack like this. So this stack is anode, separator, cathode, 100 layers. And that's our battery. And that's what allows us to put on 100 resistors. Now, If those 100 resistors were all the big ugly ones I showed you earlier, it wouldn't work either. So we have to find a micro resistor that does the job. This is a picture of the stack. Over here it shows alternating aluminum and copper. The separator and other devices aren't shown, but the name of the game here is to hook up all those resistors. How do we do that? Okay, first of all, we bring in a material to connect the copper to the copper. Now normally that's a direct connection, but when we put this material in the middle, it affects the connection with the resistor. This is a resistive material that allows you to connect with a 1.5 ohm resistance between the outside external copper lead, you can see down here, and the internal copper electrodes. Very special material. It is, the guy that invented this is Rob Rosen. He runs the materials group for us. This material is a special polymer, not ordinary epoxy. It's a cousin of the material that's is a white coating on golf balls. And embedded in it are resistive elements, and the number and resistivity of those little elements makes the polymer partly conductive. And the net result is if you hook up, and this acts like glue, and if you hook up copper to copper through this glue layer, you get a 1.5 ohm resistor. And that green stuff is the BrakeFlow technology, and that's how we put 100 resistors in, allow all the current we want to come out, but limit the current under super high current conditions so that it can't cause a fire in the battery by heating. By the way, Rob's group has 8 people in it, and they're working on 15 projects now in parallel, and there are 100 parts for this battery in our bomb that are engineered, maybe not as sophisticated as this, but that are engineered, not just materials you buy. So that's how we make 100 micro resistor connections in our BrakeFlow technology. That's why it's a big deal. So I'm glad you took the time to listen. I hope my slow motion explanation of BrakeFlow technology makes you understand that it's a big deal. You know, this could be as important to us as Intel Inside was to Intel. And I really feel that people don't get how big a deal this is. Thanks for listening.